So today we are going to talk about critical appraisal. So what that means is that we are basically going to be discussing about what are the things that we should look for when we are reading a research article that is using some sort of machine learning methods as a part of their analysis in that paper. And what are the things that we should look for to gain a better understanding of the generalizability of the study, reproducibility of the study, and whether we can trust the findings of the study enough to be able to believe the interpretation that the authors are making in that study. Couple of things we need to understand before we go and talk about the critical appraisal or the reporting guidelines of the machine learning research in an article. First thing we need to understand that there are some model development considerations that we need to take into account. There are many decisions that you will need to take, and you need to have a clear justification of why you are taking that decision. It cannot be a black box decision that the readers cannot understand. So the first thing you need to have a good justification of why do you even want to use machine learning method. As I have seen in the first few chapters of this lecture, is that you can easily do this prediction type of modeling, whether it is outcome being binary or continuous. You can do it using the parametric models such as the linear regression and the logistic regression, depending on which type of outcome. So why do you even need a machine learning method, right? Any suggestion why you would need a machine learning method? One problem with the scenario that you were mentioning is that if you have a large number of covariates, it is very likely that some of these covariates will be giving you the same information in terms of predicting the outcome. What that basically means is that those covariates could be highly correlated. And when many of these variables are highly correlated, it is possible that the diagnostics of the regression will not be as good, right? Because collinearity is something that regular parametric regression might not be able to handle properly. So in that scenario, as we have learned in our previous class, there are methods called lasso, ridge, elastic net. Those methods are built to deal with this multicollinearity type of issue. So as you see, it kind of is context dependent. You cannot just say, oh, I'm just going to write a paper where I will use machine learning. You need to understand the data first, and you need to understand what are the problems of the data and why some of the machine learning methods could be better equipped to deal with these issues. Another aspect is that, generally speaking, historically, the parametric models, and by parametric, by the way, I mean linear regression and the logistic regression. Using the parametric regressions, we generally handle a few number of covariates, and we generally go to the doctors or the neurologist and stuff like that to get the subject area expert knowledge from them to get an understanding of what are the covariates that we need to use in our prediction model, right? But as you know, nowadays we are dealing with large health administrative data sets where they routinely collect longitudinal information about the patients. Whenever a patient goes to hospital, does anything, everything gets recorded as long as this gets billed, right? So whenever you go and do a diagnostic test, whenever you go check your doctor and things like that, everything gets billed and everything is recorded. So over time, as you can imagine, there are many different data points that are accumulated over in the large health administrative data, and these data sets or data points are basically calculated as some sort of ICD-9 and 10 codes, which are the standardized codes that are used all over the world. So for example, if you are going through a particular diagnosis, then there will be a particular ICD-9 code or 10 code assigned for the diagnosis. So later, whoever is charging for your bill, exactly by looking at the diagnostic code, that person will know that what you are doing or what type of diagnostic test you are going through. So But these are living paper trail, right? Or electronic trails, and researchers later can use those data sets to build their prediction model. One of the problem with these type of data is that these data sets are not designed for research purposes, right? So for example, whenever we are doing clinical trial, we are properly designing the clinical trial, we're properly incorporating the inclusion criteria and exclusion criteria, everything, right? But these data sets that are being collected, these are collected for everybody, whoever is in the system, right? And so it is very hard to tailor that data to make it a data suitable for research, right? So you have to have a very clear understanding of what is your target population, to whom you are going to generalize these results and all of that. You have to make sure all of that to make any kind of research. And that is why obviously we have free data nowadays, almost free data compared to clinical trials. Clinical trials take a huge cost to run clinical trials, time, energy, money, resources. But these are already there for billing purposes, right? So you can just take the data and do your research. But you have to be very careful about doing this research, because these data sets were not really collected for research purposes. Whatever was related to billing purposes, they were collected. So you can imagine there are a lot of covariates that you should have had for your research purposes. When you were designing your research, you would have those variables measured. But for billing purposes, those variables are not really important, right? So something very basic, such as smoking, that is not in the admin data, health admin data, right? But for your research perspective, you know that smoking is basically a risk factor for many, many, many diseases, right? But something so basic is not even there. So that kind of tells you the picture that obviously we are playing with these data sets, but you have to be careful that the purpose and intent of collecting those data sets were very different than your research, right? And you have to be careful about that. All right, so coming back to the point of when we are using parametric models, some of the aspect was that we generally talk with the subject area experts and try to get a sense of which predictors we should include in our model. But given that now we have access to huge number of data sets and huge number of variables, sometimes the subject area expert might not be able to tell appropriately whether this particular ICD-910 code is a good predictor for the outcome that you are trying to assess. So for example, your outcome could be cardiovascular risk event, and you just did a very particular test that your doctor asked you to do, and you do not really know, or there are so many different codes. An expert might not be able to tell you properly that these particular codes are relevant and these particular codes are not relevant. So this is very hard to tell. But for the machine learning methods, machine learning method does not care about subject area knowledge. All it cares about is the correlation, whether these two variables are correlated or not. And that machine learning can do very well. It can identify all of the variables that are associated with that outcome. And it can also tell some of these variables are has almost nothing to do with the outcome. So it can not clearly, but relatively more easily distinguish those variables compared to the subject area expert. Think about if you hire a doctor now to say which variables are important for you or not, and you have like 2,000 variables, the doctor will quit in the first day, saying that I do not know all of these variables and the relationship of all of these. And the other thing that is important is that obviously we have done many research in cardiovascular research, and the doctor might be very knowledgeable about what are the main factors or the key driving factors that are giving rise to the risk of cardiovascular event. But maybe there are some new covariates that nobody has thought of before and did not really research on. But the machine learning method does not really care about what was researched on and what was not. Whether it is correlated or not, it will just pick it up, right? So for machine learning method, these are the advantages. And in the era when we are dealing with a large health admin data sets, these machine learning or these automated methods could be of some assistance. Maybe after machine learning method identifying that variable, the doctor can then think and then find a relationship between those variables, right? So that part is immensely helpful for us, that some sort of non-human intervention automated methods are telling us maybe these are the variables that you want to look into. All right. One of the other important aspect is that in the data sets that these logistic regression or linear regression methods are dealing with, these data sets are known as structured data. By structured data, I mean that there is the obvious matrix, there are some number of covariates as columns, and there are a number of observations as rows, and there is a square type of matrix that we are dealing with, right? But beyond that, there are many other data sets that are also collected or stored within the health admin data sets or other data sources that we have. One of those are, so for example, image data. Whenever there is a scan going on, taking a picture of you, it could be a radiology or it could be some sort of other scanning that you have. All of these are image data. Like there is no direct way of converting those image data to tabular data, like a matrix form, right? And our logistic regression and linear regression models are not really well equipped to deal with those kind of data. Not that only. Say, for example, when a doctor comes to see you in the hospital, they make some notes, right? And those do not get digitized very often. But those notes have values, right? Maybe the doctor said that maybe this patient has this, so test this and test that. So this text data that we often do not really take into account in our logistic or linear regressions, these writings may have some value. Machine learning methods have ways to process these text data sets. Natural language processing and all of these things that are developed within the machine learning, those could be helpful to integrate these information on top of all of the other tabular information that we already collect, right? So this image information, text information, all of these things that we have, machine learning methods are actually equipped, and we have that technology today. We are not talking about later we will develop. No, we have the technology already today. Think about Tesla and all of this, like the self-driving car, all of these are happening because of computer vision and all of these things that are already existing in our technology nowadays. And those same technology could be used within the framework of machine learning that the parametric models are not going to be able to deal with it directly. So the whole purpose of this discussion is that obviously we could, if we wanted, we could use the parametric regression models, but there are some obvious advantages of machine learning methods. And whenever you are writing a paper where you are using machine learning methods to analyze your data, it is absolutely a good idea to convey to the readers why you are choosing this particular machine learning method, right? There could be many, many different motivations. Maybe the data is highly correlated, right? Then you would just use the lasso, ridge, or elastic net type of methods. Maybe it is very hard to identify the functional form or the interaction terms and stuff like that. Maybe then you would use the card type of method. Maybe you want to incorporate the text data or the image data that the regular methods does not take into account. All I'm saying is that you have to be very clear about what is the justification of you picking a particular machine learning method. All right, so just because you know machine learning does not necessarily mean that you have to use machine learning method. So this is one of the common misconceptions that we have, is that since I already know cart method or the bagging or boosting method, I do not have to use this logistic regression model anymore. Not necessarily true. So there has been a systematic review that was done, and it showed that when people use simple logistic regression to build their clinical prediction model, and then they use the machine learning methods to build the clinical prediction, there was not a clear sign that one was doing better than the other, right? So one thing we have to understand is that machine learning methods, however powerful they are, we do not have full understanding of these, whereas this logistic or linear regression, we have been using them forever. So we know everything about how to utilize them to get information out of the data, right? So as I said, there might not be any advantage, but you have to be very clear from the beginning why you are using that particular machine learning method. If you have the justification, even after that, if there is no clear benefit of using machine learning method, that's not your problem. Because you have started with a clear research question, and you have started with a clear solution that you thought was going to solve the problem. And eventually, if the results did not really was not different, that's not really a big deal. You tried based on the best available information that you had available with you. One of the things that I always tell to my students is that forget about methods. Methods are just tools, right? Some sort of different type of hammers that you have. The most important thing is, what is your research question? Then from that research question, try to think about what are the methods that are going to solve some of the problems that you are getting in answering that particular research question, right? So, I mean, I know that after this class, like if you are going to do any kind of regression, you would just say, oh, instead of regression, why not let me just try the XGBoost method or something like that, right? And there is nothing wrong with trying that, right? Maybe to impress your supervisor, or maybe to impress the journal editor or something like that. So you can do that, but all I'm saying is that you have to have a clear justification why you are doing that. Otherwise, like, the science is not being benefited. You are just doing something like just because you want to try. So this is another consideration when you are developing your model. One of the consideration is that you have to pre-process your data. Remember, in the Caret formulation, there is a pre-process part where you could center your data, scale your data, as I have showed in the previous class. And those pre-processings are usually helpful to bring more stability in your regression. By centering, I mean just subtract by the mean of that particular predictor. And by scaling, I mean just dividing that variable by the common standard deviation that you have. And this can bring more stability. And for continuous variable, if your continuous variable is highly skewed toward one direction or the another, which is not like symmetric type of distribution, sometimes they can be problematic. And sometimes, as you know from your basic stat courses, you can do all sorts of transformations, right? Like the log transformation, square root transformation, Box-Cox transformation, and all of these transformations that you can do to make those variables look less skewed, so that eventually when you are running your regression, the residual plots will probably not look as horrible if you do this kind of transformation. One of the concern about transformation in regression method is that if you transform a variable, maybe the interpretation of that variable gets lost, right? Say, for example, if you have an income variable and you do log transformation, and eventually when you try to interpret the relationship between the income variable as well and the cardiovascular event, maybe you will have a harder time interpreting that result. The prediction model is that we do not really care about the beta coefficient of the predictors, right? All we care is the prediction itself, the y hat that we get out of the machine learning prediction or the regression prediction at the end. And one of the common problem prevailing within the medical literature is that, and this is coming from the regression, by the way, that people try to dichotomize or categorize everything. Whenever they see a continuous variable, they feel the urge to dichotomize or categorize that variable immediately, right? So say, for example, I have this continuous age variable, but people feel the need to make it like 5-year or 10-year type of categorization all the time. And that comes from the need to interpret the covariates to some extent. But as I have mentioned, the interpretation of those covariates within a prediction model does not hold a lot of water. So in that particular scenario, the categorization is not encouraged. And not only in the machine learning literature, even in the multiple linear regression, as you can see, this is a paper from, my understanding is that this is a very old paper from 2006, and they're saying that dichotomizing continuous predictor in multiple linear regression is a bad idea. And that same idea can be translated into the machine learning literature as well. So what happens is that whenever you are dichotomizing or categorizing a particular variable, you are essentially losing information on purpose. So we are hungry for information, but now we are just leaving out some information on the table, right? That doesn't make any sense if you are trying to make the best use of the data. Say, for example, you are filling out a survey, right? And when you are filling out a survey, you give some questions to a participant, and you are asking, can you tell me what is your income? The issue with that question is that so generally speaking, and it has been shown in empirical settings, that people who are with middle income, they generally do not have any problem disclosing their income level, like where their income level is. People are at the very high end, they have problem with disclosing their income. Also, people who are at the very low end, they have problem disclosing their income. And if the situation was this, that only people at the higher end was having problem with disclosing their income, then whoever was missing, we could automatically think, oh, maybe this person is a high income person, that's why they're not disclosing. But the problem is the problem is coming from two directions. Like the people who are at the lower end, they're also not disclosing their information, right? And that creates a problem in the sense that when you are trying to do the analysis, like what do you do with this data set? Like, do you say all of these are high income, all of these are low income? But that's not really true. Some of these are high income, some of these are low income. So things are happening in many different directions. So one of the things you could try to do to mitigate this situation is that you can say, okay, I basically do not have that information, right? So what can I do? I cannot go back and ask. I cannot even track down those people. So one thing that I will do, I will just delete the observations who had any missing value in their reporting. So what that would do, say for example, you are surveying with 1,000 subjects, and then you found that 600 subjects did not respond to one of your questions in your survey. So eventually you will only work with these 400 people who have answered every single question that you have asked in that survey, right? Do you see anything wrong with that? Target population is actually a very important thing here. So if you are trying to get a better sense of what is happening with the BC population, and you are certainly removing half of the population or some part of the population from the analysis, you are going to get a very skewed or biased result, obviously. Like some of the results that you are getting are not really representative of your whole or entire population. One thing you can hope that maybe the higher income and the lower income are at the same level so that it cancels it out. But there's just a hope. You cannot say objectively that is going to work. And generally, it does not work, to be honest. Maybe there are more lower income people, or maybe there are only few higher income people and stuff like that. Right? So the second strategy people take is that they say, okay, I had 1,000 people and now I'm working with 400, so I'm losing a lot of power. So why not I try to make use of the whole 1,000 data, but the way I would use that data is that I will just impute the mean value in the places where they have any missing values. So what that means is that instead of imputing lower value or the higher value, we are just imputing the mean value. And what it does is that it's not really changing any information in the data, but you are just allowed to use more observations in the data, right? The problem is, again, that is a biased result in the sense that you are not really getting all of the information that you really need, and you are imputing some information that you know are not true. Those people who are not reporting are not necessarily the mean income level people. They are either lower or higher and stuff like that. So that is obviously another problem. Okay, so that is a problem we have identified. So one thing people do is that they say, okay, let's just consider two different extremes. And what are those two extremes? Let's assign in our first scenario that everybody is poor. Like whoever said that we do not want to report income, let's just say everybody is poor and we get one estimate, right? And then in a second scenario, we say, let's just say everybody is extremely rich, right? And then we get another estimate. And we then say that maybe our result lies between these two extremes, right? But again, I mean, that is also in some way, sometime you will get very wide range, and that will not be very informative for you to make any kind of decision because the range is so wide, the result is almost unusable. So, okay, so one thing then people started thinking that maybe we do not have to be so simple. We can try to use the data to our advantage, right? Because in our survey, maybe there was not only one information, maybe there were other information, and based on which we can try to figure out at which income level this person belongs. So say, for example, we look at the zip code and try to figure out, like, is in this zip code, what is the mean income level for the subjects, right? Or some other information, like, is this person employed, like what kind of job this person does and stuff like that. If this person is someone who is like a working in a say, for example, superstore, in a teller job, we can kind of get a general sense of what is the income level this person has. Or if this person is like working in Wall Street, like we can try to get a general sense of what this person's earning is. So not only this, like we can take advantage of the whole data set and try to figure out, like we can simply try to make a regression out of it. And we can try to say, okay, based on the complete data, we know we can fit a regression, and then we can use the data set that are not complete to predict what is the income, right? So that can be a more sophisticated method of trying to impute the missing observation. So we are not relying on only one or two information in the data. We are using all possible things that can happen in the data, and that can be a more sophisticated way of imputing. Do you think that is the best we can do?
You do some clustering relevant?
Could be, yes. Could be.
Two groups, right?
Yes. So you could try to cluster based on all of the other covers to find out like which income quantile they belong to and stuff like that. That you can do. The problem with the imputation is that you are imputing something and you are treating, like after you have imputed, you forgot that these are not real values. These are just some made up values based on your best prediction, by the way, but these are still some made up values. It can still be possible that your regression is not completely right. Someone whose earning level is like 4 million, it could be like 800,000 or something like that in your regression according to your prediction, right? So it is still a made up value. It is not exactly accurate. But when we are running our regression, we are treating it as if it was real value. Why? Because like we are not distinguishing between the values that were clearly reported versus the values that were not reported at all, right? So we are obviously making some judgment error in that sense as well. Okay. So then what the researchers say, and another problem is that because we are treating the values as the exact values, as the observed values, the standard error that we get out of that kind of regression would be smaller because we are just saying that this is the value. There is no variability in there. So like with certainty, we are saying that these are the values and we are getting our observations or the predictions or the estimates. So to mitigate this issue of variability, what we generally do is that based on all of the other covariates, we do not assign just one value. We try to find a distribution of values that could be possible for income for this particular person, right? So from regression, we try to find a distribution of values. And so say, for example, in that regression, you could say that person's income level is between 20 to 40, right? And we do it kind of like an iterative scenario. We know that the distribution is between 20 to 40, and then we try to impute one value out of that distribution in your data. So for example, now we impute 30. And then we have that data, and then we do all of the analysis and we have our results. And then we impute another time from the 20 to 40, we input another value, say for example, 35. And then we do all of this analysis and we get our prediction or the estimate of the coefficient. And we do, say for example, we do it 20 times. We like first we input 30, 35, 40, 20, 25 and stuff like that. We input all sorts of value based on the distribution that we have determined is the true distribution of the income, potential income that person could have. And then once we have all of these results, then we simply pull the results together to get a general sense. And what that does is that you still have the predictions similar, but the confidence interval is slightly wider. And this is representative of the fact that you are dealing with some observations where you are not exactly or 100% sure. So there was some uncertainty there, and your slightly wider confidence interval would take into account of that uncertainty. So one of the things that I mentioned here is that obviously this class is not about teaching you missing data analysis, and this is just a byproduct that I'm just talking about. If you are more interested about missing data analysis, I have like 8 video lectures. If you have the time after this course, maybe you can obviously go there and take a look at this is the YouTube playlist that I'm linking here. So the point that I was trying to make in here is that they have done a systematic review on the machine learning methods, and they found that the machine learning, because obviously many of these data science folks that are coming into this data science world, they are not necessarily familiar with the missing data analysis problem or the statistical issues with them. And so what they generally do, they only do complete case analysis. That means that they just chop off the data wherever they had any kind of issue, or they do the mean imputation. What that means is that if your income was like all over the place, just take the mean and just input them every time. But both of these, as I have explained, both of these approaches have their own problems. So what the recommendation was is to use the multiple imputation methods to deal with this type of issues. Or you might be lucky, depending on which method you are choosing to do your machine learning analysis. Say, for example, if you are dealing with some sort of tree-based methods actually have their inbuilt capacity to impute the variables first or the missing values first before getting to the analysis results. So if you are using some sort of tree-based methods, that could give you some better estimate compared to this complete case or mean imputation approaches.